Hello everyone, I'm TszOn from the University of Hong Kong. Today I present UPA, a differential privacy system for big data queries, such as Apache Spark queries. Given a query and an input dataset consisting of many data records, UPA automatically enforces differential privacy to any individual data record in the input dataset. Differential privacy is a powerful technique to preserve the privacy of any individual record in a dataset by adding noise to a query's output value. Let's take a look at the following example. Suppose Bob is a medical researcher in a hospital, and he can query the hospital's patient's medical dataset. Here we assume that patient's medical records are anonymized, and Bob cannot directly access the information of any individual medical data record. He can only obtain the aggregated information of the medical dataset. One day, Bob knew that Alice entered ICU in that hospital, and he knew that Alice was the only person that entered ICU on the 1st January of 2019. Bob can leverage this auxiliary information to count the total number of patients that entered the ICU on the 1st of January 2019 while having certain symptoms, in order to find out Alice's symptom. DP aims to address this issue by adding noise to the query's output, that is the count number of patients, to prevent privacy leak through Bob's query's output. DP adds noise to a query's output value according to a crucial parameter called sensitivity. Sensitivity is the greatest change on an output value of a query when the data record is added to or removed from the input dataset. Given the input dataset and some query in this slide, the sensitivity is apparently 4 because removing the data record of value 4 changes the output value the most, which is 4. However, identifying the data record that changes the output value the most for a large dataset is fundamentally difficult and requires brute force approach, which runs the same query on the same input dataset repeatedly. Each time remove only one input data record from the input dataset. It is extremely inefficient and impractical. Existing approaches make other trade-offs to infer sensitivity value more efficiently. Existing approaches are divided into manual approach and static approach. Manual approach requires a sensitivity value to be inferred and given by human. It is general, but it is inaccurate and not automatic. Static approach statically analyzes a query's syntax to infer a sensitivity value. It is automatic, but it is not general, and it is also inaccurate. Currently, the only static approach is Flash. We argue that we don't want to trade off automaticity, accuracy, and generality for efficiency, and only brute force approach has all these features except efficiency. Hence, we start from brute force approach to build UPA while solving its inefficiency problem. Our main observation is that brute force approach computes on mostly overlapped dataset. I will give you the definition of overlapped dataset in the next slide. And big data operators' commutativity and associativity properties and sampling theories can substantially reduce the computation on the overlapped dataset, and hence tremendously enhance the efficiency of brute force-based approach. We found that brute force approach computes on mostly overlapped dataset. Take this figure as an example. Suppose we want to identify the influence of each of the first 3 individual data records in this input dataset on the sum query's output. Brute force approach removes these 3 data records individually each time. As we can see, the remaining 5 data records are repeatedly computed. Hence, our goal is to reduce such redundant computation. To achieve this goal, our first observation is that big data operators are commutative and associative. Commutativity means an input dataset can be computed in any order. Associativity means that an input dataset can be partitioned into subsets, independently computed and aggregated. Take this figure as an example. Similar to previous slide, suppose that we want to infer each of the first 3 data records' influence on the sum query's output. By using traditional brute force approach, the remaining 5 data records will be repeatedly computed. To reduce such redundant computation, by leveraging the commutativity and associativity properties of big data operators, we can first compute the output value of the 5 data record, which is 10. Then, we will use such computation results to compute the influence of each of the first 3 data records on the sum query's output. Hence, the redundant computation on the 5 data record is greatly reduced. Note that in addition to the sum operator in this example, big data operators such as mean, mass, joint, filter are all commutative and associative because these properties are essential for a big data processing system to provide good parallelism and fault-tolerant mechanism. However, even leveraging the associativity and commutativity properties of big data operators, if we have to compute the influence of every individual data record in an input dataset, the efficiency is still very low. Our second observation is that for any size of big dataset, UPA only needs to sample 1000 data records and compute each of their influence on a curious output. In order to accurately infer a sensitivity value, it is because existing work shows that the influence of a data record on an output value usually follows normal distribution, and statistical theory show that 1000 samples are sufficient to accurately identify these samples' underlying normal distribution. Hence, given a big data set of any size, UPA always sample 1000 data records and treat the remaining data record as the overlapped data records. UPA then computes a curious output value on the overlapped data records and reuse such output value to compute each of the sample data records' influence on the curious final output value, as well as the corresponding sensitivity value. UPA is an end-to-end DP system that is fully integrated with Spark. The table below shows a set of DP-enabled Spark-compatible MapReduce operators API, such as Map and Reduce. UPA can also be integrated with other big data systems, such as Hadoop and DryLink, because these system operators are also commutative and associative. For the evaluation, we use a cluster of 5 computers. We compare UPA with Flash, the only related work that automatically infers a sensitivity value. Our first evaluation metric is accuracy, the root mean square area of the sensitivity value computed by UPA of Flash compared to the ground truth. The second evaluation metric is performance overhead, the additional execution time of UPA compared to vanilla Spark. The evaluated workload consists of 9 real-world queries that are often evaluated by related work, which include count, machine learning, arithmetic queries. Note that the evaluated workload includes all the 5 open-source benchmark queries that were evaluated by Flash. UPA supports all the 9 queries, while Flash only supports the 5 count queries. Because UPA is a brute force-based approach, so UPA can infer a sensitivity value for any type of big data queries. Flash is a static approach which is only applicable to count query. This figure shows UPA and Flash RMSE on the 9 queries. The y-axis is RMSE in log scale, and the x-axis is the query's name. The figure shows that the average RMSE of UPA is 3.81%, 5 order of magnitude lower than Flash. It is because UPA is a brute force-based approach, which infers a sensitivity value based on a query's control flow and data flow, while Flash is a static approach which infers a sensitivity value only from query's syntax, which ignore the query's control flow and data flow. Because the sensitivity inferred by UPA is close to the ground truth, UPA enforces end-to-end DP. Now, we look into UPA's performance on large dataset size. This figure shows UPA's performance overhead on 120 GB dataset size. UPA on average incurs 77.8% performance overhead, because UPA only needs to compute the influence of each 1000 sample records on a query's output. Although this performance overhead is non-trivial, it is worthwhile because UPA already greatly enhanced the efficiency of brute force-based approach, while being as automatic, accurate, and general as brute force approach in enforcing DP. So here comes our conclusion. UPA enforces end-to-end DP automatically, accurately, and efficiently by leveraging the big data operators' commutativity and associativity properties, as well as sampling theories. UPA has the potential to greatly promote the adoption of DP in real-world big data analytics, such as medical analysis, recommendation system, fintech, etc., effectively protecting the privacy of user data. All UPA source code and evaluation results are available on this link. Thank you.